Good afternoon. I'd like to welcome all of you to the first in the Della Pietra lecture series. This is a lecture series that was made possible by a generous gift of Stephen and Vincent Della Pietra and their families, and I would like to start by thanking them for the opportunity that this provides us to make lectures like this possible. The idea of the lecture series is, well, let me start this way. The Simon Center here at Stony Brook brings together a great collection of world-class mathematicians and physicists working on some of the most interesting and exciting problems in these two fields and in their intersection. And with a resource like that, it's natural to use the resource to reach out beyond what we think of as our core constituency, which in this case is the members of the center and visitors, the math department, and the physics department. So what the gift from the Della Pietras makes possible is for us to leverage this center to reach out to the rest of the community, to interested students on Long Island, to other scientists on Long Island, to the general public on Long Island, to try to explain to them, inform them about some of the latest and most exciting results in physics and mathematics and how physicists and mathematicians think about these very deep and fundamental questions. So to do that, we need to find speakers who are, on the one hand, top-notch scientists working at the cutting edge of their science. Well, there's a collection of those, and we tend to know that collection. But at the same time, we need somebody who's able to explain to a much broader audience, communicate the excitement, the basic ideas in a way that gets across to them what this enterprise is all about. Well, there are certainly people that can give beautiful public lectures, but the intersection of these two sets is very, very small, and it's out of that that we want to pick our Della Pietra lecturers. So let me just explain a little bit the format today, which each lecture will have a slightly different format and lectures aimed at slightly different audiences depending on the lecturer and so on. But today we have two talks. The talk you're at right now is more a colloquium style lecture aimed at our core mathematicians, physicists from our sister units and the members of the center, and others, scientists who have enough background information, background knowledge in these areas to get something out of the colloquium style talk. Later on this afternoon at 5:30, Brian is giving another talk, which is a general public talk aimed at high school students, Stony Brook undergraduates, and the general scientific and public community. All of you are welcome to come back to that talk. It will be a talk hopefully understandable by the much wider audience. So as I said, we have two criteria, and the intersection, the people that satisfy both criteria, is very small. But as soon as the Della Pietras came forward with this idea for a lecture series that included an outreach, there was one obvious candidate that sprang to my mind, and I think probably sprang to all of our minds, and that's Brian Greene. So Brian, I first knew Brian when he was working in the part of string theory and physics. It was very intimately connected with some of the most sophisticated mathematics, Calabi-Yau threefolds, mirror symmetry, and so on. His work today is, at least as far as I'm aware, is more at the relationship of string theory and cosmology. He's a professor of mathematics and physics at Columbia University, and he's the head of IceCap, the Institute for Strings, Cosmology, Astroparticle Physics. So it's my great pleasure to introduce Brian to you. The title of his talk is The State of String Theory.
So thank you very much. It's a pleasure and an honor to be here. I was realizing, thinking about the lecture as I was coming into that, I've known Stephen and Vincent for over 30 years, and it's shocking enough that I could know anybody for over 30 years, but that's how it goes, I guess. So it is an honor to be part of this lecture series and to be the kickoff speaker, so thank you for inviting me. The talk that I'll give this afternoon is about the state of string theory, and the one change relative to what I was planning to do is Jim told me that he has to leave halfway through to meet with a previous appointment, so I'm going to talk twice as fast in order to try to get through this quickly. I will try to basically give you a sense of where string theories come from, just to sort of get us all on the same page, and then I'll switch gears to give us a sense of the various achievements that string theory has been able to reach over the last few years and decades. The summary that I give will necessarily be one that's peculiar to my own interests. If somebody else were giving this talk, they would focus on other developments. So this won't be fully comprehensive by any means, but I think it will give a feel for where string theory has gotten as of today. Okay, so basic way to think about the major developments in physics is that most of the lasting contributions in physics have emerged from some kind of conflict. Either a conflict between theory and experiment, or sometimes between theory and theory. And out of the tension of conflict often has emerged some new breakthrough in how we think about how the universe is put together. Now, the three major conflicts that are relevant for the conversation today, the first is between classical mechanics and electromagnetism. All of us who recall our basic physics remember that according to classical mechanics, there's no speed limit at all, but you look at Maxwell's theory and you find that there's this absolute speed that emerges for the speed of light. How to make those two ideas compatible, that was the tension that drove Einstein in 1905 to develop the special theory of relativity. But that particular development, I guess it must be key to my words. There it is. Is it me? Am I beeping away, or is there something else beeping? No, not beeping, because it's just in my head, which is much more disturbing, but I'll learn to live with it. Okay, so special relativity wound up being in conflict with the classical theory of gravity that Newton gave us, because again, in classical gravity, you have the gravitational force exerted from place to place effectively instantaneously. There's no time parameter in Newton's equations. How do you reconcile that with the speed limit set by light that comes out of special relativity? And that, of course, through 10 long years of work, led to the general theory of relativity, one of the most spectacular insights really of all time. That, however, set up an even deeper tension, an even deeper conflict, because Einstein's general theory of relativity winds up being in conflict with quantum mechanics. And that is the deep conflict that I'll be talking about here, and trying to address the question of how do you resolve this particular conflict. And of course, as most of you know, there are those of us who think that string theory is at least a candidate for what the solution to this particular conflict might be. So just as a quick outline of the things I'll now talk about, I'll do a quick primer on string theory, again, just to get us pretty much all on the same page. It'll probably be old hat for most everyone. I'll then turn to a status report where I'll cover about 5 or 6 areas and try to give you a sense of where we have gotten versus where we'd hope to get and what the hurdles are to achieving success in those areas. And then I'll finish up with just some summary and conclusions and a bit of a look to the future. And the look to the future that I'll give actually won't be one that necessarily looks, 100 years to the future. It'll be actually one that looks about 10 minutes to the future, because it naturally will lead into Hiroshi Oguri's talk at 4:15. So these things really dovetail, not by design, but maybe just serendipity, that they all kind of come together, which is great. Okay, so for part 1 of the talk, string theory primer, in the 1970s, string theory was introduced as a theory of the strong interactions, the force that keeps nuclei bound together inside the nucleus of an atom, the quarks bound together ultimately inside of the protons and neutrons. Now, in that particular guise, string theory didn't do a particularly good job. Quantum chromodynamics came along, and basically string theory was swept to the side. And often when a theory is swept to the side, it's just gone, right? It's rare for a theory to be resurrected. But in this particular case, string theory was resurrected pretty much in the 1980s as a model not for how the strong interactions work, but how all forces work, a model for a unified theory of all forces and, in fact, all matter as well. This work was all done in a perturbative framework, a perturbative approximation. And what the next major development that we can peg more or less to the 1990s till today is going beyond the perturbative treatment in the 1980s to a non-perturbative framework, which has given us a lot of insights, and I'll be describing some of those to you today. Now, just in terms of the particular problem that string theory was seeking to resolve and why it was resurrected in the 1980s, here's a way to think about it. So, let me focus upon the force of gravity. We have Newton's view, of course, of gravity that we teach our high school students, Physics 1 students, this notion of the force of one body acting on another in a completely mechanistic manner where we have basically an action at a distance type framework. And that conflict that I described earlier on, in that we need to have a theory that's compatible with special relativity, where gravity is not communicated instantaneously. And it was Einstein in the general theory of relativity that did that. And he did it, of course, as we all know, by introducing a new player into the game, space-time. And it was space-time curvature and the warps and curves in space-time that communicates the gravitational force. And this approach is borne out by observation, so it is a spectacular step forward to a deeper understanding of how gravity works. However, as I mentioned at the outset, the discovery of general relativity gave rise to its own particular conflict, because once space-time becomes a real physical entity, it is subject to all of the laws of physics that every other entity in the physical universe is subject to, and that means it's subject to quantum mechanics. And the thing about quantum mechanics is that whereas Einstein is envisioning space-time to be a nice, smooth geometrical object that can be described by the Riemann tensor, Riemannian geometry, and so forth, quantum mechanics tells us that on very short scales, there isn't this nice, smooth structure to deal with. Instead, quantum mechanics is a discrete, fuzzy type of picture of the microworld because of the uncertainty principle. And that winds up setting up the conflict. A way to think about it is this. Imagine a simpler system, just an empty box of side L. An empty box of side L, because of quantum fluctuations, there's always a non-zero amount of even the magnetic field. Let's start with something simpler, not gravity, but the magnetic field. Even in an empty box, we know that there is a fluctuating magnetic field whose size of fluctuations goes like 1 over the square of the size of the box. You can test this, the Casimir effect and so forth. You can really measure this. This really happens. Now, applying that same very simple idea, not to the magnetic field, but rather to the gravitational field, well, first of all, the gravitational field is associated with space-time curvature. So if the gravitational field is fluctuating, that means curvature is fluctuating. And a similar back-of-the-envelope calculation tells you that the size of the curvature fluctuations goes like 1 over the cube of the size of the region, where the numerator is this particular number, the number called the Planck length, which tells us that on length scales shorter than the Planck length, which numerically is about 10 to the minus 33 centimeters, space-time will not have a nice, smooth geometrical form. Instead, it'll look something like this. So I don't know if you can lower the lights a little bit, but if you imagine just magnifying space so that you're able to examine it on shorter and shorter scales, the idea is on the shortest of scales, around the Planck length, it'll look something like this in this schematic form, and it's hard to do Riemannian geometry in this particular background. So that makes it pretty clear that Einstein's ideas are an effective description of space-time on large scales, but on short scales, something has to give, something has to change. And that is mathematically shown to be a real issue when you do calculations and you find that when you try to put gravity and quantum mechanics together in the simplest of ways, you find nonsensical results. You find divergent results from many of your calculations. So this is the deep conflict that I was referring to in my opening slide, the third one, between general relativity and quantum mechanics. And this is the one that we want to resolve. Now, before resolving it, a question that we should address is, should we care about this conflict? And the bottom line is that for many practical questions, you don't need to care about this at all. Physics is perfectly happy just keeping gravity and quantum mechanics separate because there are many interesting domains, physical problems that you can make great headway on without having to put those two theories together. And that's why physics has done very, very well over the course of many, many decades, even though there is this issue at hand. But if you are interested in having the true underlying theoretical framework of physics, then clearly you can't have a fundamental framework with two ideas that are incompatible. Something has to happen to either change the theory in some dramatic way or make those two ideas compatible. And to make that even more concrete, there are certain physical questions where you have to put gravity and quantum mechanics together. Cosmology, black hole singularities, more general space-time singularities, where you've got very short scales but strong curvature. You need both gravity and quantum mechanics. And if you don't have a theory that's able to put them together, you won't be able to make progress. So that's why you should care these kinds of issues. So that is what propels us to try to resolve the conflict between gravity and quantum mechanics. And string theory is one of the most prominent approaches that has been put forward. So let me say a few words about string theory. It's a unified description of all forces and all matter. The basic framework for that is to remember that in the standard model of particle physics, we have the strong, the weak, the electromagnetic forces. Let me put gravity in there for good measure for a moment, but I'll come back to how it's described in a second. Each of those in the standard model is described by a particle. The strong force communicated by gluons, weak force by the WZ bosons, electromagnetism, of course, by the photon. And on top of those particular particles, we also have the matter particles, electrons, quarks, neutrinos, and their heavier cousins. In the standard model, we have a very powerful quantum field theoretic description of these three forces and all of these particular particles. But there are a number of missing pieces. There's no explanation for why you have all of these disparate forces and disparate particles. There's also no explanation for about 20 parameters inside the Lagrangian of the standard model. You just have to do experiments and set those parameters. So the goal would be to go beyond the standard model by understanding those parameters, understanding the structure, and most importantly, putting gravity into the story because, again, this is a quantum field theory, and quantum mechanics and gravity are like oil and water, so you need something that can allow gravity to enter the story. And that's where the string theoretic description comes into the picture. The idea of string theory simply being, imagine that all of these particles are actually different modes of vibration of some new fundamental entity called the string. Different modes of vibration would give rise to different energies, different masses, different properties, and so on. And the goal would be to envision a theory, string theory in particular, in which each of these particles can be realized in the schematic form that I've shown here. Indeed, when you study the math of string theory, you do find that this kind of structure emerges, and most impressively of all, there is a particular string vibrational pattern that has all the right properties to be the graviton, the particle of the gravitational force, and that's why we believe that string theory is a quantum mechanical theory that involves gravity as well as the other forces of nature. Now, to have a bit of intuition before we move on to the status report of why string theory succeeds in this quest to put gravity and quantum mechanics together, a rule of thumb way of thinking about it is this. In the standard model, in point-particle quantum field theory, interactions, consider the electromagnetic interaction, they take place at points. So if you have an electron, a positron, the hours would be reversed, but electron and a positron annihilating at a given spot, there's an invariant space-time point that all observers can agree upon as to where the interaction takes place. So roughly speaking, all the interaction is squeezed into a single space-time location. What happens in string theory? Well, in string theory, you don't have forces that operate at a unique space-time location. Instead, imagine you have a situation where you have two strings interacting to produce a third string. If I asked you to tell me where is it that these two strings touch for the first time, well, that's not a Lorentz invariant notion. You might say, well, it's sort of over here. but that's according to one particular time slicing of this diagram. If I was moving relative to this diagram and relative to your time slicing, I would time slice it differently, and according to a different time slice, the interaction of the strings might take place here or here. So in essence, string theory spreads out interactions. And that's important when it comes to gravity, because if you describe the gravitational interaction in this kind of particular point where the interaction is squeezed, where it takes place, you get divergences that we don't know how to cure. But if you spread out those interactions as string theory does, the divergences go away, and you're able to put gravity and quantum mechanics together. So then the picture that we wind up having is, rather than a bunch of point particles all interacting, you have strings interacting where they can join together, they can split apart, and so forth. And these are the fundamental kinds of interactions in a string theoretic description of the forces and the matter. Another rule of thumb way of thinking about it is, if you're familiar, of course, with the old four Fermi theory, that also was a theory that had particular problems where the divergences arose from having interactions take place at a point. Going to SU2, description of the weak interaction spread out the force over basically the inverse size of a W boson. That kind of curing of singularities that we're familiar from the four Fermi theory is what we're talking about here, where the spreading out is over the size of a string. So it's a very familiar kind of progression from a theory that's not well behaved to one that is well behaved by spreading out interactions. And that's really what makes string theory tick. A couple of other key features before we turn to the status report. When you study string theory, the actual equations, you find that there are no adjustable dimensionless parameters. And that's a rare thing in physics. Normally our physical theories have all sorts of dimensionless parameters that you can adjust so that the theory matches data. Here, you don't have it. So in principle, this is the most predictive theory that we have ever had our hands on. In principle. And I say in principle because when you study it in a little bit more detail, you find that there's another interesting feature, which is that the theory requires more than 3 spatial dimensions. And that fact, that the mathematics is internally inconsistent unless there are more than 3 spatial dimensions. In the perturbative framework that I'm talking about here, you need 9 dimensions of space and 1 of time for 10 space-time dimensions. What I'll show in just a moment, the particular form for the extra dimensions in some sense plays in practice the same role as adjustable dimensionless parameters do in, say, the standard model. So while in principle string theory is highly predictive, we'll see that this fact is what gets in the way of that. So how do you make sense of a theory that requires more than 3 spatial dimensions? Well, that's something that we've learned to deal with even from the early part of the 20th century in so-called Kaluza-Klein theory. You just imagine that some of the dimensions are big. That's the grid part. That's the part we know about. But some of the dimensions are compactified, very small. So we have more difficulty seeing them. And this is an example where you'd say have R3 cross S2. That isn't what string theory really says for the form of space-time, but it's a good picture to have in mind. Instead, the more precise form for the extra dimensions, this is one example of a Calabi-Yau manifold, Ricci-flat complex Kähler manifold, vanishing first Chern class. Of course, this is a 6-dimensional space through which we take a 3-dimensional slice and a 2-dimensional projection, so there's a little bit of distortion, if you will, in the picture that, but it gives you sort of a feel for what the extra dimensions in string theory look like. This is the, for those of you that care about the details, the quintic hypersurface in CP4. So this would be roughly what space would look like in this setup. It'd be R3, the grid, cross a Calabi-Yau manifold, and this is the kind of space-time that string theory draws our attention to. Now, the reason why the extra dimensions are vital, both from the point of view of physics and predictions, is that the precise size and shape of the extra dimensions have a profound impact on the physics of string theory. And why is that? Well, the rough way to think about it is, you know, if you're doing quantum mechanics on R3 cross some compact space, the wave function that you're dealing with has support not just in the R3 but also in the compact space. So when you're solving, say, the Schrodinger equation, there's a part of the Schrodinger equation that lives on the compact part of that manifold. And therefore, if you're looking for eigenfunctions and eigenvectors, the precise size and shape of the extra dimensions will play a key role in finding the eigenvalues of the Hamiltonian. A little bit more precisely, if you imagine starting with a 10-dimensional field that's massless, it's worthwhile, in order to see the implication of the form of the extra dimensions, to expand this guy in an expansion where you have 4-dimensional modes times 6-dimensional modes. X is 4 coordinates, y are the 6 coordinates, and break up the 10-dimensional Laplacian in a parallel way. Then you note that the resulting equation turns into a tower of equations where the 4-dimensional mass of the 4-dimensional part of the field comes from the eigenvalue of the 6-dimensional part of the field under the 6-dimensional Laplacian. So there you see directly how the compact part of the space plays a key role in things in principle that you can observe, 4-dimensional particle masses. So that is the framework that we are led to, and if we had a unique form for the extra dimensions, we'd have a unique set of predictions. The problem is that we don't have a unique form for the extra dimensions, as I will now describe. But this is meant to be the end of part 1, the brief review of string theory, why we are led to it, and its basic physical setup. Any questions on that before I move on to the status report? Okay, so let me just check. Anybody speak English? You good? Okay, good. Okay, that's always important. Okay, so let's move on to the status report, and I'd like to talk about 1, 2, 3, 4, these 6 areas. What string theory has to say, how well it's done in terms of particle phenomenology, some of the non-perturbative developments in the theory, experimental tests, perhaps the most important part of the talk, singularities, black holes, and its implications in mathematics. So let me begin particle phenomenology. So as I've just quickly reviewed, we've noted that observable 4-dimensional physics should be determined by the extra dimensions. So the natural question is, what does this physics look like? And how close does that physics come to the things that we see? So how do you answer a question like that? Well, ideally, we'd have a theoretical framework that tells us what the precise form of the extra dimensions is, and then we just calculate away. The problem is, I mentioned that the equations of string theory tell you that the extra dimensions in this perturbative framework need to be a Calabi-Yau manifold, but there are many Calabi-Yau manifolds, and we don't have any way of picking out one over the other. So what we do is, you do perhaps a bottom-up approach. Just go over to the catalog of Calabi-Yau manifolds, open to page 1, and start doing your calculations. And if you do your calculations on the first Calabi-Yau manifold, as people did some years ago, you find physics that looks nothing like our world. Wrong number of generations of particles, wrong gauge groups, things of that sort. But you say to yourself, that's just the first Calabi-Yau manifold. Let me go on to the second. And you find nothing that looks like our world too. And you keep on going, and a few thousand graduate students later, you don't laugh, I was one of those graduate students. You find a given Calabi-Yau manifold where when you do the calculations, you find physics that looks something like our world. Maybe not exactly right, but maybe the number of generations in the gauge group are on target, and that encourages you to keep on going. And you keep on going, but most of them look nothing like our world. And then sometime later on, you find an example that looks damn close to our world, And that encourages you that there's a chance that string theory can describe physics that we observe. But you say to yourself, this wasn't really what we signed up for, right? What we signed up for was a theory that would make predictions, not a theory where you kind of just keep turning the pages and see what comes out next. So what do you say to yourself? Well, certainly in the perturbative framework that people have been studying in the 80s and early 90s, there was nothing that seemed to pick out one Calabi-Yau over another. So the assessment then was that we kind of had what I mentioned earlier on, a loss of the hope for predictive power, because in practice, even though there aren't these free dimensionless parameters as you find in field theory, the free parameters of the standard model or of quantum field theory more general seem to be replaced by choice of solution, a choice of the extra dimensions. And the hope was that a more precise non-perturbative understanding of string theory would cure this. And that's what we needed, a non-perturbative understanding of string theory. So that propelled people onward to try to develop non-perturbative formulations of string. This is the only reason, but this is one of the reasons why a non-perturbative formulation seemed to be critical. So let me now turn to a status report on where things have gone in formulating string theory non-perturbatively. To do that, let me take a step back and just remind you that, bless you, back before 1995, there were actually 5 distinct string theories. Their names aren't all that important, but what is important is that each of them was understood perturbatively. So each of these theories had an expansion parameter, so this might have been for the type 1 theory, and all observables that we calculated in a given string theory were calculated in the traditional manner, just some power series expansion, assuming that that parameter was quite small. And when one did these calculations, it was pretty clear from these perturbative expansions that these string theories had a lot in common. They all involve strings, extra dimensions, gravity, quantum mechanics, all were a part of these theories, but they differed in detail. So the observables that you calculated in each of these theories just were different from one another. So it was as if you had groups of individual string theorists huddled around each of the different string theories, doing their calculations and finding results that were relevant only to their particular version, their particular flavor of string theory. An interesting question was, what would happen if the coupling parameter in any one of these theories was to get big, isn't small? Most people would say, we don't know. We just don't know how to handle it whatsoever. But a few intrepid explorers took on that question and found something really remarkable. Found that as the coupling parameter in any one of these theories gets big, the theory basically continuously transmutes into one of the other string theories with a small value for its coupling, a phenomenon known as duality, which leads to a picture in which these 5 distinct theories, at least in the previous way of looking at things, are really all joined together as the coupling parameter of each is allowed to get big. And I just want to show you again, because it took me a long time to figure out how to do that. Okay, good. So the idea is that these 5 theories should now be thought of as 5 perturbative windows on one single theory. And I think as many of you know, that one single theory is called M theory. One of the reasons it's called M theory is because when one studies some of the new insights one gets from being able to make the coupling parameters of arbitrary size, one finds that there aren't just strings in these theories, there also are membranes, extended objects of 2 or 3 or 4 or 5 and so forth, number of dimensions. So string theory is not just a theory of strings we learned from this particular development, it's also a theory of membranes, one potential meaning of the M in M theory. Now, in terms of actually understanding the mathematical structure, the true underlying equations of M theory, what has been done there? Well, 2 developments. Let me just show one quickly, and then I'll move on to the second. One of the earliest proposals by this group of authors was to show that in a fairly well-defined sense, M theory could be reduced to a kind of quantum mechanics. It's a quantum mechanics of n by n matrices as n goes to infinity, so it's not the most calculationally friendly approach to being able to define the theory, but there is a framework in which one believes one has the fundamental Hamiltonian of the theory. The other way of thinking about the mathematics underlying this non-perturbative formulation of string theory comes from Maldacena and then many others as well, where he showed something that is, I think, one of the more remarkable developments of all in string theory, that strings on a particular spacetime, happens to be anti-de Sitter 5 space cross S5, is absolutely identical to, dual to, something that is much more familiar, namely a quantum field theory that exists in a 4-dimensional space-time, has a certain amount of supersymmetry, it's conformally invariant. Those are just details. But the point is, you have a string theory on one space being dual to a quantum field theory on another. So the picture to have in mind, and Hiroshi will show you better pictures of this later, is that you can imagine having an object, say, in the interior. So string theory as applied to this apple would be equivalent to quantum field theory as to describe to these degrees of freedom that are living on the boundary of this space. A very strange identification, but one way of thinking about its utility is that you can use the quantum field theory on this boundary as a definition of string theory in the interior. So here in principle is a non-perturbative definition of a quantum theory of gravity in the interior in terms of a non-gravitational theory on the boundary. Very unexpected and very surprising. The lesson we learn from this is that gravity, which seems to be so inherent to string theory, can be described by a non-gravitational theory on a different space. We learn that a theory in one number of spatial dimensions can be equivalent to a theory in a different number of spatial dimensions. And I'll leave it to Hiroshi to go into more detail. We describe this in terms of holography, thinking about a hologram as a thin piece of plastic that can encode a three-dimensional scene. It's in essence this boundary space with this particular description is able to describe physics in a higher dimensional space in the interior, much as a hologram does. So the overall assessment, even if you don't follow all the details, is that there has been tremendous progress in formulating a non-perturbative description of string theory. I would say, I don't know if everyone agrees with this, but if you would have asked me 20 years ago, would we have gotten this far in finding a non-perturbative formulation of string theory, I would have said no, but yet here we are. So certainly we have a ways to go, but it's more progress than I, for instance, would have predicted. Okay, so with this progress on formulating a non-perturbative understanding of string theory, let's go back and see whether it gives us some insight into the particle phenomenology, the question of what is the shape for the extra dimensions in string theory. And the bottom line is that the problem that we encountered in the perturbative approach, that we didn't know which Calabi-Yau was the right one, remains completely unresolved. There's absolutely no evidence at all from any of our non-perturbative understanding that there is a unique model coming out of string theory. And perhaps the way to think about this, therefore, is that string theory is closely akin to field theory. In fact, we just saw a moment ago that there's a sense in which string theory and field theory are the same, because they're dual to one another. But maybe the thing that we know about field theory is that there are many, many, many quantum field theories, and there appears to be one that's relevant to the low-energy particle phenomenology that we can do at places like the LHC. Maybe there are many, many, many string theories, and there's just one that's relevant to our world, and it's just a matter of finding it in the same way that we found SU3 cross SU2 cross U1, the standard model from quantum field theoretic techniques. In fact, there is a new perspective that these insights have given us that comes both from observation and from theory, and it's particularly relevant for today because it involves dark energy. As we have understood the Calabi-Yau compactifications in more and more detail, we've recognized that there was a dressing, there was an additional feature of Calabi-Yau compactifications that we weren't taking into account back in the 80s and 90s, which is that there can be flux, there can be gauge flux that threads through the non-trivial cycles of a Calabi-Yau manifold, and that can give energy to the space. Normally, if you have a Calabi-Yau manifold, you can vary its moduli, its shape and size continuously without any cost in energy. But if you got gauge flux that's threading through the manifold, then when you start to change it, well, now there's going to be an energy cost because you're affecting the gauge flux that's wrapping around cycles. And that wound up giving an interesting picture for the space of Calabi-Yau compactifications that looks something like this. It's called the landscape. And the idea is that there's a distinct amount of energy. You can think of it as the cosmological constant from a four-dimensional effective space-time perspective. So the height here would be the cosmological constant, the amount of dark energy in the theory. Different choices for the Calabi-Yau and different choices for fluxes would give us different semi-stable points in this large landscape of possibilities. And roughly speaking, because the typical Calabi-Yau manifold is something like 500, a few hundred distinct cycles, and you imagine the fluxes can vary over discrete values from roughly 1 to 10 before the back reaction is too strong that we can't really handle it, that gives us roughly 10 to the 500 distinct possible forms for the extra dimensions, 10 to the 500 distinct possible heights in this big landscape of possibilities. Now you hear that, you're like, 10 to the 500 different possible string models, you know, what can that possibly be good for? Well, one thing that it may be good for is this. If you imagine that the amount of energy in each of these in natural units varies between 0 and 1, and if you've got 10 to the 500 distinct possibilities, then you can argue pretty convincingly, as some string theorists have, that there's going to be a value very close to the value that has actually been observed. and for which the Nobel Prize was awarded today, right? So Perlmutter, Rees, Schmidt, their teams measured the dark energy in space, surprisingly found that was non-zero. Its value is about 10 to the minus 120 in natural units. The question is, how do you explain 10 to the minus 120, such an odd, weird number for the amount of dark energy in space? One possible explanation is, well, in this framework, you're guaranteed there's going to be some compactification where the energy is 10 to the minus 120 because you got 10 to the 500 possibilities spread in an interval between 0 and 1. So the picture that this suggests is something like this. If you combine this with ideas of eternal inflation, imagine you have universe, inflating universe after inflating universe, each with a different form for the extra dimensions, each with a different amount of dark energy. And that may be a framework in which you can explain that particular observation. Highly controversial. Not everybody believes that this is an approach that really makes full sense. But it is one of the ideas that is pursued in trying to make sense of the inability to locate one specific form for the extra dimensions in string theory. Okay, so that's pretty much where we've gotten on particle phenomenology. Let's turn to the important question of experimental tests. And the nice thing about this part of the talk is that it's pretty quick. So we can just move on. Well, let me just give you a little bit more detail. So there are potential experimental tests that wouldn't falsify string theory, wouldn't prove string theory right, but certainly would give string theory a shot in the arm. So for instance, in string theory, many of the low energy models are supersymmetric models. So the LHC is looking for supersymmetric particles. The data is becoming uncomfortable for low energy supersymmetry. It's not ruled out low energy supersymmetry, but the parameter space is shrinking as the work takes place at the LHC and nothing new is found, but we just have to wait and see. Possibility of black hole, microscopic black hole production, a natural implication of certain versions of string theory. Look for those also, not yet found. RIC, so right nearby, using this ADF-CFT correspondence that I was describing before, certain difficult, strongly coupled gauge theory calculations on the boundary can be described in terms of gravity calculations in the bulk. And indeed, as many of you no doubt know, if one looks at the shear viscosity of the quark gluon plasma divided by its entropy density, you find that the best calculations so far for what that measured value should be come out of the ADF-CFT correspondence, describing that gauge theory in terms of gravitational dual. Very interesting, very impressive. Other possible experimental signatures, people have envisioned that strings could get stretched out by certain cosmological processes, and they could be out there wafting in space, giving off gravitational waves. Looking for those as well. Possibility that gravity on very short scales is modified by having additional dimensions in string theory. The 1/r² force law, of course, requires 3 spatial dimensions. More dimensions, that could change. But the two that I just want to quickly show you some pictures of are the last two, brane world models and some signatures that could come out of cosmology. So the idea of M theory I was mentioning is that the M stands potentially for membranes. We learned that there are these large sheets in string theory. So you can imagine that our universe, what we have called 3-dimensional space, may actually be a 3-dimensional brane floating in a higher dimensional environment, with the interesting property that comes out of string theory that the strings out of which you and I are made are trapped on our 3-dimensional brane because they've got endpoints that are anchored in our particular sheet of space, if you will. But there can be other strings that don't have endpoints, namely loops, and those are generally associated with gravity. And those gravitons can leave the branes, as indicated in this picture here, and that's something that you can look for at the LHC. Smash particles together, try to create gravitons that leave our brane, a missing energy signature. Again, nothing yet found, but it's a possible way where you might get experimental contact between things that are being done at accelerators and these kinds of theoretical models. As far as cosmology, it's something that I've been working on for a little while. I'll just give you a quick summary of it, which is, might we be able to see signatures of string theory in the cosmic microwave background radiation? At first sight, you'd say, well, that'd be kind of a weird place to look. Strings are kind of small. Why would you look at them over there? But bear in mind that in standard inflationary models, the universe goes under at least 60 e-folds of inflation together with 10 to the 28, a factor of 10 to the 28 expansion after inflation. So conservatively, since inflation, the universe has undergone an expansion of a factor of 10 to the 54. In most models, it's much bigger than this. In fact, imagine that it's a good deal bigger than that. The reason why that's an interesting number is that the size of the universe in Planck lengths is about 10 to the 61, which means that for all but the most conservative models, if you look at any length scale that we have access to today and run it backward in time, in the early universe, it was sub-Planckian in size. If it was sub-Planckian in size, that means the exotic physics of string theory or quantum gravity or something else could have affected its physics. The standard calculations of the temperature fluctuations in CMB absolutely assume that traditional standard quantum field theory works to arbitrarily short scales, something that we pretty much know is not true. So the question is, can you parameterize some of the changes that might occur by imagining that new physics comes in the trans-Planckian domain? And I and others have done calculations that suggest there could be other tiny temperature fluctuations of a factor much smaller than anything yet observed, but potentially accessible to the Planck satellite. So if those were to be found, that would be exciting too. Okay, so that gives us the ability to assess where we are in terms of the hope to experimentally test string theory. There are potential signatures that could give some insight, but giving the most hard-tack assessment would be that there are no experiments or observations to date that give us evidence that this theory is right. However, I would say in the same breath, the whole notion of string theory being right is almost a funny idea once you know that it's directly connected to quantum field theory through the dualities. In that sense, how could you ever prove string theory wrong? It is quantum field theory, just in a particular different guise. But in this more traditional way of thinking about string theory and it making direct contact with observations, no, there is nothing that one can put their finger on as of yet. Okay, two other areas of progress. Space-time singularities and black holes, a little bit more formal than the things that I was talking about over here. So where does string theory stand in that regard? Well, there are many singularities that general relativity cannot handle that are now well understood in string theory. Even back in the 80s, certain kind of orbifold singularities, take a space, divide through by a discrete group of isometries, you get conical singularities. These were understood well in the context of string theory, something that general relativity would have difficulty coping with. Another collection of singularities where S2s in a space are shrunk down to zero size. Those were well understood. More drastic kind of singularities that, if there's time, I'll return to in a moment, called conifold singularities and conifold transitions, where an S3 collapses down to zero size. Those are also well understood in string theory. Those are singularities where we have a cone over an S2 cross S3 base, and we have a singularity at the tip. And the question is, can you make sense of physics in this environment? And the answer is you absolutely can, even though Einstein's equations would break down. But in addition to other singularities, the real big question is, what about the black hole type singularity, the Big Bang singularity? A lot of progress on these, but I would say that still quite an open question. But the overall assessment would be, certainly in this domain, there's been great progress from string theory in understanding many different kinds of singularities that previous techniques couldn't deal with. Now, as far as black holes go, I can't resist but giving what many consider one of the most striking achievements of string theory, which is an understanding of black hole entropy. So back in the 1970s, Bekenstein and Hawking showed us that black holes have an entropy that goes like their area over 4 in natural units. The puzzle for 25 years was to find those quantum states such that if we count them when we take the log, the usual formula from statistical mechanics 101 holds, namely that the log of the number of quantum states is the entropy. So what are those microstates and how do you count them? Nobody really could figure that out until Strominger and Vafa showed that if you take a collection of particular membranes that came out of the M-theory understanding of string theory, you could, at weak coupling, find a collection of branes whose microstates you could easily count. And then they found that if you increase the coupling constant, make it stronger and stronger and stronger, this collection of branes would collapse into a black hole. In essence, gravity is getting stronger. A black hole's area you could calculate. Now, they argued that since this is an integer, this count of microstates, it can't vary continuously. Therefore, the integer that you count over here, if this is meant to be a correct physical setup, should give you the entropy on this side, and indeed, when they did the calculation in detail, the log of the number of states you count over here is equal to the area of this fella divided by 4. Sort of a spectacular insight that's been taken much further since then. But here we see, again, a very basic test. If string theory were really missing some fundamental degrees of freedom, it's a little hard to imagine how these calculations would come out bang on, which is, again, an encouraging step forward in trying to believe that string theory is telling us something real about the world. Final area, string theory's contributions to mathematics. Well, there have been many. Mirror symmetry, enumerative geometry, quantum algebraic geometry, four-manifold classification. Many of you know a lot about a variety of these. I'm just going to give a quick summary of the first two, just because they're my favorite. So, what is mirror symmetry and its role in understanding aspects of enumerative geometry? Well, mirror symmetry is the idea that you can have two distinct Calabi-Yau manifolds, call them M and W, that even though their topologies may be different, geometry is different, that these guys would give rise to absolutely identical physics, something you wouldn't really expect at all from Einstein's general relativity. In general relativity, there's a one-to-one correspondence right there from the form of the equations between the metric on space-time and the physics that that metric would give rise to. But the idea in string theory is that that map need not be one-to-one. It, in this case, is two-to-one. So let me just quickly give you a sense of where that comes from. When you're describing strings moving in a Calabi-Yau background, the typical way of describing it is a nonlinear sigma model where the Calabi-Yau manifold is M, and you're looking at a nonlinear sigma model built on the world sheet, the two-dimensional world sheet that's swept out by a moving string. And it turns out that's a superconformal field theory. I don't want to get too bogged down in the details, but just to note that the superconformal algebra contains within it a U1 left cross a U1 right, allowing you to label all of the states, the vertex operators in the theory, in terms of their eigenvalues under those U1 transformations. And when people studied in detail the map between the geometry of the Calabi-Yau manifold and the physics of the superconformal field theory, the dictionary between them had a particularly striking form. The harmonic 1-1 forms on the Calabi-Yau manifold were mapped to fields whose charges were 1 and 1, but the 2-1 forms were mapped to fields whose charges were 1 and -1, which raised a little bit of a puzzle because the difference between a 1-1 form and a 2-1 form is pretty dramatic, but the difference between charge 1 and charge -1 is basically just a convention. So why was there such a pronounced difference in the geometry and such a trivial difference in the physics? And that led some to suggest that maybe we were missing half of the story. Maybe that is, one given physical model might have two different geometrical incarnations, two different nonlinear sigma models giving rise to the same physics, with the idea being that in one of them, the map that I've shown you is as I indicated, but in the other it's reversed, so that the 2-1 forms would go to the 1-1 charge objects and the 1-1 forms would go to the reverse, in this way restoring a nice symmetry between the geometry and the physics. Now I should say, when this conjecture was first made, I certainly thought it was not true, because I think there's a much simpler reason for why we would look like you're missing half the story. It's simply that you, in string theory, don't just specify the manifold, you also specify a bundle on that manifold. Implicitly, you're choosing that bundle to be the tangent bundle here, but if you chose it to be the cotangent bundle, then exactly this interchange would happen in the dictionary. So my view was nonsense, not true at all, until we were able to find an explicit construction which showed that it is true. So we were able to find a particular conformal field theory such that we could apply a certain operation on it that produced a new conformal field theory. That operation was functorial in the sense that it applied as well to the underlying geometrical manifold, producing a new nonlinear sigma model on O of M, namely W. And the striking thing is, for particular choices of O, we were able to show that this conformal field theory that you get via this operation is actually isomorphic to the conformal field theory you started with, even though these two manifolds are completely different. Which means, putting it all together, that this nonlinear sigma model and that nonlinear sigma model are absolutely giving one and the same physics. Moreover, when you looked at the dictionary between this conformal field theory and that one, they're isomorphic, but what's the map between them? The map, in fact, just reverses the sign of that charge, which means at the geometrical level, the 1-1 forms on one manifold are swapped with the 2-1 forms on the other, and vice versa. And that's what mirror symmetry is. Two Calabi-Yau manifolds related in this manner, that gives rise to one and the same underlying conformal field theory. Now, why is that useful? Let me give you one example just to get a feel for it. When you do a calculation in string theory, say a 3-point correlation function, if you've got two geometrical interpretations of one and the same physical model, well, you can give that observable two different geometrical realizations. And it turns out, in particular 3-point functions, that the geometrical version of that particular observable is a fairly complicated expression that involves integrating 1-1 forms against each other, summing over rational curves, and so forth. A fairly complicated looking expression. Whereas on the other side, it's a very simple expression, basically something that can be calculated by variation of Hodge structure. And the remarkable identity that comes out of the equality of these is that this expression must be equal to that expression. Now, when we wrote down this equality some years ago, it was striking, but I didn't think anybody would ever evaluate it. And that's where I was wrong, because Candelas and his collaborators, a couple of years later, were able to take a 3-point function, calculate it in this way, expand it in this form, and in that way read off the number of rational curves on any Calabi-Yau, but in the first case was the quintic in CP4. And let me just note what they found. So the answers for the degree 1 and degree 2 curves were known to mathematicians at the time. For degree 3 curves, it was not known. The math calculations that came from that physical identity produced this number. Around the same time, two mathematicians, Ellingwood and Strama, were doing these calculations, and they came up with a different number for the number of degree 3 curves on the quintic hypersurface. There was a bit of an argument at MSRI, actually, where the physicists sided with the physicists and the mathematicians sided with the mathematicians, until Ellingwood and Strama found a bug in their computer code and sent around a message saying that physics wins. So indeed, the result that comes out of this calculation is correct. And the wonderful thing, of course, is you just look back at this formula, you just put this in Mathematica, and you just expand it, and you just let it crank out these numbers. So it's not something that you have to invent new techniques order by order, degree by degree. You just keep on counting degree 15 curves, degree 17 curves, degree 22 curves. You know, I just need to keep it this. Sorry, 6 should be a 5 over here. So, but you see how powerful this is. Now, since this, mathematicians have found ways to prove these formulas, Yau and company, and all sorts of credit issues, whatever. You know, my view is that, you know, this comes right out of the physics, and there you see how string theory makes an unassailable contribution to mathematics in a very, very concrete way. Now, there's one thing else I wanted to do, but I'm a little bit out of time, so I'm only going to race through it. It has to do with topology change, but unfortunately, if you want to ask any questions, I'm happy to, but let me just wrap up to see where we... So if you understand what I'm doing here, you don't need me to say it. And if you don't understand what I'm doing here, you wouldn't understand it anyway. So I'll just go through. Yeah, I spent a lot of time, obviously, on pretty pictures, you know, deformation, small resolution, good stuff. Yeah, topology change. Yeah, okay, but, you know, whatever. Okay, so the bottom line is, let me... now I'm like going a little too far. So what I wanted to get to was this thing right over here. Kind of report card, if you will, for where string theory stands. So as far as unifying gravity and quantum mechanics goes, I just can't seem to get the hang of this. There we go. So as far as unifying gravity and quantum mechanics goes, is that required in any theory that is meant to make progress? Well, certainly it is. And string theory does an excellent job of that. In terms of unifying other forces, the strong, weak, and so forth, electromagnetic, do you need a theory to do that? No, you don't necessarily have to have a unified theory of all forces, but string theory naturally puts them all under one rubric since they're all communicated by vibrating strings, and therefore the status of that contribution, I think, is unassailably excellent. What about incorporate key breakthroughs from the past? You know, it's certainly historically true that new developments in physics typically build on the past. They don't wipe out the past. And string theory in my mind, rather remarkably incorporates almost all of the key breakthroughs in particle research from the past 30, 40 years. Gauge symmetry, family structure, symmetry breaking, it all has a natural home within string theory. So from that point of view, it's excellent. But on these issues, explaining particle properties or giving rise to some experimental tests that can be observationally confirmed, certainly that's required. And at the moment, it's indeterminate because there are no ironclad predictions that string theory really comes out with. As I gave you, there's some ways in which string theory might be able to make contact with experiment, but it's still very much up in the air. Back to some of the more formal developments, curing singularities, black hole entropy, and the mathematical contributions, I think that on that particular score, string theory does very, very well. So the bottom line is, it's up to you to figure out your own answer to this particular question. I am quite encouraged by the developments in string theory. And moreover, when we recognize from the ADS-CFT correspondence this tight association between string theory and field theory, this other cartoon that you've probably seen actually is not as silly as it sounds, right? If string theory and field theory are in some sense the same structure, just analyzed in different ways, then the traditional approach of field theory would be string theory. It's just a different way of analyzing and deconstructing the theory. So as far as the future goes, I started early on with this particular slide, 70s, 80s, and 90s, but the missing question is, what about now going forward? And let me just give you one thought on that, and that, as I mentioned, will lead naturally to the next talk, not mine, but to Hiroshi's. So there's a wonderful class of developments that didn't receive a huge amount of attention in physics until recently, from people like Jacobson and Padmanabhan and folks of that sort, showing that Einstein's equations, in some sense, can be derived from a thermodynamic starting point. And in fact, Eric Verlinde, responsible for getting people more interested in this most recently, showed that if you think about the drive of a system to go to a higher entropy state, there's a way in which you can imagine that drive toward a higher entropy state is an effective force that's acting on the system. And he argued in an interesting paper that gravity could be thought of as an emergent force, and a force that in essence is just the drive of a system to maximize its entropy. So from this perspective, gravity would not even be a fundamental force. It would just be something that emerges from a more fundamental starting point. That dovetails in an interesting way with another class of developments that go back to 't Hooft and Susskind, where they argued that gravity really should be described in a holographic framework. This is before Maldacena, arguing that the physics of black holes, where the information loss issue could be resolved if you imagine that when an object falls into a black hole, its information is in some sense stored, smeared out on the surface of the black hole. And that idea of information on the surface being able to describe physics in the interior is again a holographic idea, which then culminates really in Maldacena's recognition that you can have a gauge gravity duality, that is the CFT ADS duality, which suggests that this idea of holography is quite general, and maybe therefore space and space-time themselves should really be thought of as an emergent object that comes from a more fundamental starting point, and that may be where things are headed going into the future. So I will stop there. Thank you very much.
Questions?
You left out string theory's competitors on your report card.
Well, when I used to get a report card from school, there wasn't a competitor on my report card. What kind of school did you go to? Yeah, no, it's a fair question. Are there any? Yes, there are. Loop quantum gravity, I guess, is an approach that certainly has been pursued for a long time by people like Ashtekar and Smolin and Carlo Rovelli and so forth. And, they have been and they are strong proponents and enthusiastic about their approach. I've not studied their stuff in great detail, but the times that I've looked at it, I've not been as compelled by their approach as by string theory. Some might say that their approach has made progress in a different class of problems, trying to formulate a background-independent approach where you don't have an ambient space-time around which you are perturbing, which is what a lot of the calculations in string theory have been like, rather trying to build space-time from the ground up. So I'm glad that there are different approaches that are being followed, and we'll just have to see how it all turns out. So, I think the health of a field is partly reflected in the different sets of ideas that people are pursuing to try to solve the same problem. So I think it's great that there are other approaches. I'm also glad that I'm working on the right one. But,
You didn't mention proton decay as a prediction of string theory. Is it essential to string theory?
No, I mean, depending upon the form, say, of, just to be concrete, the form of the compactification, the low-energy effective theory that follows from that compactification can have a range of different features. There are some in which the proton is highly unstable. Those would be models that would clearly be ruled out. There are others in which there can be, again, similar things to those that you're familiar with. There can be discrete symmetries that can protect proton decay from dimension 5 operators, which can reduce the decay rate so that the lifetime is sufficiently long. In supersymmetric gauge theories, supersymmetric standard model, proton decay is sufficiently long that we wouldn't expect to see it, as you would, say, in SU5. So there's nothing really that one can say. There are models where it would decay too fast. There are models where it wouldn't.
What is the recent CERN experiment like?
The recent CERN experiment meaning this neutrino business? Well, yes. So, it's surprising for the phrase faster than the speed of light to emerge in a context of a motion of a massive particle. So if it were true, I think many of us would be very surprised by that result. I think many of us believe that, as in many previous attempts to suggest that special relativity is not right, this will go away in time. Again, this is a complicated, messy experiment to measure a very clean and simple number. You'd think that the way you measure the speed of something is, you mark it, set, go, you fire it, and you just measure how long it took to get over a given distance. That's not really what happens here. You've got protons that slam into a graphite barrier that then produces mesons. The mesons travel a while, then they decay statistically into neutrinos. The neutrinos then travel from Geneva to Gran Sasso. You don't even know which neutrino it is that you actually detect at the detector because you don't know which meson produced it. They claim that they've taken all this into account. These are smart, creative, innovative people. So they claim, we've done all that. We've taken it all into account. We know what we're doing. But for instance, the neutrinos get there 60 nanoseconds early. That's not a lot over 450 miles. If they've measured the distance between Geneva and Gran Sasso off by something on the order of, 50, 60 centimeters or so. That'd be an impact on the results. Have they taken into account that the moon pulls on the Earth's crust and can change distances a little? Have they taken into account that the light that the GPS satellites use to pinpoint locations, well, the speed of light in vacuum is one speed, the speed of light in air is another. Turbulence in the air can affect the speed of light. So there are all sorts of messy, messy elements. I'm sure they've taken it all into account. But I would need to see a completely independent measurement before I would really take it seriously. In fact, I would bet anything that I hold dear that it's wrong.
That answer your question?
I'm just wondering, is there anybody who feels differently about those results? Just curious. But, yeah, okay.
So just speaking about CERN, I heard they were looking for the Higgs boson.
Yes.
Does string theory say anything about that? I don't think you mentioned anything.
Well, again, there are compactifications that naturally give rise to spin-zero scalar fields that could play the role of a Higgs boson in the low-energy field-theoretic model following from these string theories. So string theory is compatible with the existence of a Higgs particle. There are versions of getting low energy physics from string theory that don't need a Higgs particle, that try to break symmetry in different ways. The standard model, of course, is based on the idea that there is a Higgs particle, and I think most of us have been firm believers that the Higgs particle exists, and as the data is, the noose is tightening around the neck of the Higgs particle, it becomes a little bit more uncomfortable. If you don't find the Higgs particle, there's a way in which that'd be very exciting. I mean, string theory could work without a Higgs particle, so this wouldn't, in any way affect what I'm talking about here. But it would affect the last 30 years of thought on the standard model, and it would be exciting to get a result that's incompatible with the last 30 years. In essence, that's what we live for, things that are unexpected. The challenge and the fear in some level that I have is, if the LHC finds nothing new, that would be very exciting and interesting, because there has to be something new. Our perturbative equations of field theory break down. There has to be some mechanism for breaking symmetry. So if it doesn't find anything that we predict so far, it means there's something more exotic happening. But how do you go to a funding agency and say, we found nothing, and we are so excited that we need $10 billion more to build the next machine? So that there is another political issue that potentially comes into play if that is what happens. But maybe it's still early in the game, though, and they may well find exactly what one anticipates.
After the advent of the landscape, where you can sort of get any kind of parameters you want, has it basically made the theory unfalsifiable, or are there some correlations that are true in any area of the landscape?
It's an interesting question you ask, because there are different answers that one could give for that. I mean, I found this cartoon, which I find totally offensive, but bringing that to mind, there is this question that was asked over here, which is, by making string theory ridiculously malleable with your 10 to the 500 different ways to compactify the extra dimensions, have you put the theory beyond falsifiability? Now, one answer is that the string theorist kind of gets fed up and kind of, so I don't even want to show that, completely not my perspective, completely inappropriate response. But I would say this. There are some that say, okay, 10 to the 500, you can get absolutely anything in there. It's not so obvious to me that you can get anything in there. I mean, Mike can weigh in on this. 10 to the 500 in this space is actually relatively sparse. These are discrete points in a large space. You do enough. You do 1,000 right measurements, you could nail down what those points should be, and then your next measurement would be something that could falsify the theory, number one. Number two, I think that one of the things that needs to be done in string theory, I mean, a program that Mike really was responsible for setting up in the first place, is maybe what we need to do, at least at this stage, is have a better statistical understanding of what's out there, because these theories could be clustered in interesting bins, where maybe, if you understand the mass of the low-energy particles, they're not sort of uniformly distributed among all possibilities. Maybe they're bunched in interesting groups that would allow you to make some statistical prediction about how many universes would have this or that property, allowing us to see whether our universe is or is not likely in this theory. And if it was a highly likely theory, that would give you some sense that you're getting some insight into why things are the way they are. The problem, of course, is it's hard to do that. I mean, Mike set out this program, but it isn't something by any means which is complete. And moreover, then if you want to find specific theories in order to judge them based on data, well, there are a lot of theories, and it's just too hard to analyze them in any systematic way. So I think there are technical hurdles, but I don't think it puts it beyond falsifiability.
One last question.
So along those same lines, I confess that it wasn't until, I guess, 40 minutes ago that it occurred to me the intellectual connection that you pointed out between the arbitrariness of the parameters that go into the Lagrangian of a familiar theory and the choice of manifold and that sort of thing in string theory. What is the philosophical difference, if there is one, between the two? Because it seems all of a sudden to me that our choice of standard model is, in a certain sense, just as arbitrary, and it's just as many, if not more, possibilities.
Yeah, the one philosophical, and I wouldn't call it, the one scientific difference between them is the parameters in standard model Lagrangian, you generally view them as numbers that are set by experiment. when you look at how those numbers arise in the low energy effective theory to string theory, they typically arise not as fixed numbers, but as fields whose expectation value gives you a particular number. So it's more of an issue to have additional fields whose values aren't set versus a fixed number whose value you need to set. And that's sort of the main difference between one and the other that perhaps I skated over a little bit in drawing a link between the two. But beyond that, in terms of assessing whether the theory is right or not, just as you really can't prove the framework of quantum field theory wrong unless like you violate CPT or some basic symmetry is violated, you can always find a field theory that's going to be able to describe the data that comes out. That may be the way to think about string theory too. And Mike has another one to add to that.
Add to that, whereas, as Brian said, in the standard model of field theory, the numbers that you measure, here the fact that they come out as fields and as properties of the extra dimensions means that there's still hope that we could find dynamics that actually determine them, or determine which ones are very likely. So very early in cosmology, our universe was created out of something. The other possible universes could have been created out of something. Maybe the type of universe we see is more likely than the others, and maybe someday we'll know how to calculate that and prove it or disprove it. So I think that there's much more hope against string theory than might have been in the theory of fundamental parameters.
Exactly.
All right, let's thank Brian.
Thank you.